Thank you for joining us today for September's GPSX webinar. Today the plan is to talk about using the GPSX define function. It maybe is a somewhat underutilized or underappreciated feature in GPSX. This is something that will allow you to create some new variables out of the existing set that we are already doing in GPSX. And then what I wanted to do today was kind of show how you can use that feature to be able to create and identify some key process indicators, and then use those to be able to analyze what's going on in a wastewater treatment plant. So even though this is what I would call maybe a bit more of a software-oriented button-clicking kind of webinar, I've tried to work to having some really good process stuff towards the end in the desktop demonstrations that we're going to be doing. So, as always, please, if you have any questions along the way, please feel free to type them on the fly in the chat box. And what we'll do is I'll stick around at the end of the webinar after everything is done, and I'll answer as many questions as we have time to answer after we get through the webinar. Okay, so here's the agenda for today. I'm going to talk about the define function, as it is called in GPSX, and then there's essentially 6 different things you can do with it. So I've broken them into 3 different sets there: daily moving averages, mass flows, and integrated totals, and then also defining the SRT and F to M ratio for your activated sludge plant. And I have desktop demonstrations set up for all of those things as per usual. I'm going to do some hopefully interesting things with that as we go along. And as I mentioned, we'll answer any questions that you might have at the end. Okay, so the GPSX define function button is there to basically help you efficiently add new calculations to the standard set of calculations that we're doing for GPSX. So any place that you have something that you would like to sort of do an extra set of calculations on top of what we're already doing, this is where you can set some of those things up. So for example, if you had a number for your effluent BOD, you could calculate a daily average or a moving average of that. We also have mass flows that you can integrate, that you can implement throughout the plant. We have totals, that's basically integrating something over a period of time. And then custom ways to set up the definitions of the solids retention time and food to microorganism ratio for your facility in a way that makes the most sense for your particular layout and for your understanding of what those particular parameters mean. So I'll just very quickly mention up front, I have it in the slides later on. The reason we have all of this kind of extra functionality around this is particularly for the SRT definition, is that SRT is like kind of one of those things where it depends on the layout itself and on the plant that you're modeling, but also on the individual. I think the SRT means slightly different things to different people. So what we've done is, rather than just forcing a definition upon you, we allow you to define it in the way that you'd like to use it for your particular setup. So that allows you to basically define these KPIs, key process indicators, in the way that makes the most sense to you, the way that you want to be able to use them. Now, I will mention that we actually have an entire tutorial on using the define function. It's tutorial 8 in the tutorial guide. So go to help menu and go to the menus option and find the tutorial. And also all of our tutorials have already been worked out in videos on our YouTube channel as well. So feel free to pop over there and take a look at that as well. So this is a feature that's been around actually since the very beginning of GPSX, and allows you to add these additional calculations where you can create these extra things. And then at that point, once you've created them, these new variables, they are there and can be used just like any other variable in GPSX. You can output them to reports, you can put them on graphs, you can use them for controllers, and it's all there for you to be able to do. So as I mentioned before, the certain things like the SRT are not automatically already calculated for you. You have to define them. But also, we don't do a moving average of every single variable in every calculation in GPSX, partly just to keep the management of the number of calculations we're doing. It's already hundreds and hundreds of variables that are calculated even for a simple model. And then if we did on top of that, moving averages and daily averages and so on, it'd be a lot of calculations. So what we do is we say, here's everything that we got, and then you want to do some averages and mass flows on top of that, you can do that too. Now, this is, just to be clear, in addition to any other type of customized calculations that you might already be doing through writing your own custom code. So you may recall from past webinars and from our tutorial guide that you can write your own code in GPSX and get that gets compiled along in our open source platform to be able to interact with the model. So that kind of thing is not what I'm talking about today. This is a built-in feature that does not need you to write any code. You can do custom code to do the things that we're going to talk about today if you'd like to do them on your own or in a slightly different way. And we actually have a full webinar that I did just back in the summer on doing implementing custom code to create different types of control algorithms in GPSX. Okay, so the define button itself is found at the top of the GPSX window. It is this little one right here. It looks a little bit like a mathematical function. F is a function of X, that kind of thing. And when you click on it, it pulls down this menu automatically. And there's the 6 different types of things that you can define with this particular feature. All right, so let's start into talking about the averages first, daily averages and moving averages. So for any output variable in any GPSX object on your drawing board, you can set up a daily or moving average for that particular variable. If you can find it in the output variables menu, you can set it up. So this creates a brand new defined variable that will show up separately in its own brand new menu. And then you can do that for whatever different types of parameters that you want to do it for across any number of different connection points in your layout. So you click on the F to X button, and then you click on daily average, and it comes up with this type of menu here. Now, on the left-hand side, you have the streams. You have the stream connection points here labeled in the way that you would have labeled them. And so you check off one or more of those to specify the points at the plant where you would like to do these averages. And then you click on the number of different variables that you would like to perform that upon. So basically, it's going to do every one of the things you've clicked off at every one of the locations in the plant. So basically multiply these two things out. That'll tell you how many new variables that you are creating. It's pretty straightforward. And once you've done that, you just hit accept at the bottom. And then when you go to the overflow connection point for that particular object, go to the output variables menu. Down at the bottom, there will be a brand new menu that was not there before called defined variables. And then you'll see the daily average or mass flow or whatever it is that you have defined for this particular thing. So these are kind of handy. They're only there when you set them up ahead of time. That has to be done in modeling mode. And then that creates new code that gets calculated along with your model, and it gets compiled in, and then you've got new variables ready to go. So they'll look like this. It'll say, for example, daily average dot, and then the thing that you have specified. So if you do several of them for one particular connection point, you'll see them all listed in a single menu here, and you can tell them apart for the different locations by their label, which is on the left-hand side here. So you can drag those onto graphs. You can plot them in any way that you like, and then they'll also be available for you to output to your reports as well. Okay, so let's talk about the daily average. So the daily average is something that's actually calculated on the fly, so to speak. So it is actually calculated as the simulation is running, right? So basically, the simulation here, I did a dynamic simulation here. We can see the effluent total suspended solids, and you can see that those numbers are going up and down here. And you can see here, this black line is our defined moving average, right? So what this is basically a calculation that happens once every midnight. So here's 5 days along the bottom. This is midnight. So here at midnight, we calculated the moving average for the previous days. So this is done at midnight from every set of previous day's values. And then it just holds on to that value until it gets to the next midnight. And then it looks back again and calculates that day. So it's not post-processing. This is happening as you're going, which makes it a useful thing to do a controller on if you wanted to do it that way. Um, so basically you're looking back at the previous day's stuff and then it does a calculation. So just to do that kind of graphically, here's a bunch of data points that were for day one, or sorry, the second day that we have there from 1.0 to 2.0 here in the time axis. And then all of those things, we take the average and that's calculated this point right here. And then that gets held until it does a new recalculation while all of these data points were happening. And then we do a new average, and that's this data point right here. And then that gets held going forward, and so on and so on. So in this way, it's always reporting sort of the previous day's daily average, right? So it's kind of looking backwards, and it calculates at midnight whatever the previous day was. So the moving average is much similar kind of thing, but it allows you to specify the length of time over which you would like to take the average. And it is also a moving window as well, too, right? So it's not just once every midnight. So you can see here that once you've done that same process, so you click off the locations where you would like to do everything, and then you can see which things it is I want to do the moving average on. When you create your new defined moving average variable, it looks pretty much just like we saw earlier, except it has this little piece on the side here, which basically says, what is the size of the window over which we're doing this moving average, right? So that allows you to specify 1 day or 5 days or whatever it is that you want to do. So it tends to be working out as a much more sort of smoother type of curve here. So you can see as the variable was going up, the moving average was also going up, and then it took some accumulation of values coming down for it to kind of settle down. And you kind of get, an on-the-fly calculation, just like you did before, but it's from n days. You specify how many days data points that it is. So it's done and recalculated continuously. So the curve is smoother, but it's always still looking back in time, so to speak. Now, I know this is actually probably the one that gets used the more out of the two of these things, and particularly if it is used in a control context. I know it's frequently used by various people for SRT control, where they want to do not control on the instantaneous SRT that's happening right now, but rather a rolling 5-day moving average of the SRT, and that kind of keeps the system and without having some very aggressive changes to wastage, when you got this nice smooth curve to work from. Okay, so what would these be used for? So basically, you can use a daily trend if you want to sort of basically studying the course trends of what's going on rather than the individual hourly fluctuations. I know some people like it because if you have a lot of composite 24-hour composite sampling data, so it's really a number that represents a number of individual samples that were taken and mixed together in a way that's kind of equivalent to an average. Those samples together are then reported back, once per day. That's kind of like what we're doing here with this daily average, right? So it kind of lines up with the meaning of what a 24-hour composite is. And also we have this smoother process control that I mentioned, which is using a control or a PID control loop on a 5-day moving average of SRT. Now that one is fun because actually you need to do sort of two defines in a row. You basically need to define the SRT first, and we're going to come to that. Then you define the moving average of the SRT, and then you put that as your control variable, and then you got to tune to that particular thing, and so on. So we'll see what that looks like a little bit down the road here. Okay, so I should note that there's a little pull-down menu at the top here that says stream variables, process variables, etc. These are different things that will allow you to sort of change what appears in the right-hand side of the menu here. And so right now, by default, it's going to come up with stream variables, which is basically just flow and all your concentrations. So that's going to be there. But if you pull down to one of these other ones, you can get process variables, which is things like energy, airflow, the volume of the unit, like liquid volume if you have a tank that goes up and down. You also have the system variables, which are things like layout-wide operating cost, user variables. So if you make your own custom coded variables, brand new variables that you're writing code around, you can also do defines on those as well. And then the defined variables themselves, you can do defined variables on defined variables. So as I mentioned before, defining SRT and then doing a 5-day moving average on that. So that's how you get access to that other stuff. And I have a demonstration that I'll show you on that down the road. Okay, so I'm going to start with doing very simple, setting up a couple of averages here just so that you can kind of get the feel for what it looks like. So you can see here that this is a regular conventional activated sludge plant. And this is obviously an influent coming in, a rectangular primary clarifier. We have a plug flow aeration tank, and all this is set up as an MLE system. So it's actually 3 tanks in series. The first one is anoxic. There's an internal recycle. So we're doing nitrification and denitrification, plus also chemical phosphorus removal here, secondary clarifier, and then out to the effluent. So I'm just going to pop over here, just run a really quick simulation so you can get the sense of how this is working. We can see here there's our 3 zones here. That's anoxic at the front, and there's 2 milligrams per liter in the of dissolved oxygen in the second 2 zones, nitrifying, and then of course it is denitrifying. It's only 4.8 milligrams per liter of nitrate at the end there, even though we had 20 something coming in. So we're doing a decent job there. Okay, so I'm going to go back to modeling mode. So just to reiterate again, when you're doing the define button, it has to be done in modeling mode while you're building your layout. Now, you can always come back and change things and add new things or whatever you want, but it has to be in modeling mode because we're actually changing the code that gets compiled into the model. Okay, so let's do a daily average to start with. I'm going to click here. I'm going to bring up that daily average menu, and then I'm going to do a daily average on the TSS values in the primary clarifier effluent and in the plant effluent here at the end coming out from the secondary clarifier. And I want to do it for TSS, right? So here's all of these, and this is a long list. Of course, there's so many variables that are available at every one of the connection points in GPSX. So these are all menus that are closed. It's here in the composite variable menu, TSS right here. Whoops, sorry, got the wrong one. TSS, there we go. Okay, so we hit accept. Now, if I go back, as I mentioned before, to this menu, so this connection point was where I specified I'm doing an average on the TSS. Go to output variables. You can see down here, define variables. There's my new daily average thing. And I bring it up, and there it is. Daily average total suspended solids. Right. Okay, so we got to go over to simulation mode, and you'll notice that it's doing this thing here. It's recompiling the model. And so that means it's now added a few extra lines of code compared to before. And in a moment here, that'll be ready to go. And I'm going to just run a steady state simulation here. And actually, sorry, I'm going to actually run a dynamic simulation because I want to see how that average for each day works. Right. Okay, so that's just about done. I have a tab here empty and ready to go. And what I want to do is I want to go to those 2 new variables. So this one here, output variables, daily average, and I'm going to drag that to here. And I'm also going to drag the effluent one, which is from right here. Output variables, defined. There's our daily average. And to here as well. All right. So let's put it on here. I'm going to change the details of this graph here because this is average TSS. And you can see these daily average signals that are there. We don't need 1,000 on the scale. In fact, probably 150 would be enough. And so let's do that. And so let's run a 5-day simulation. I'm just going to manually change the influent flow on this slider here, just so that we have something to look at. Okay, so let's run that. I'm going to grab this thing here, and now we're going. So, and I'm going to switch it, and then you can see, of course, it only recalculates that number once every midnight. So we're only going to get 5 new numbers as this is coming along here, and that kind of tells the story of what was going on. If I had plotted, the actual TSS alongside, we would see, of course, that similar pattern, but a little bit earlier in time. But you get the sense of it that this is basically calculating that once per day. Okay, so now let's do a moving average as well. So I have to go back to modeling mode to do that. So I probably should have done these together at the same time, but nonetheless, I'm going to do the same ones here. Let's do the primary clarifier effluent solids and the final solids at the end of the plant. So that means I got to go click solids over here. Now, if I go back, we should be able to see two different things available to us in the defined variables menu. There's my daily average and moving average. And of course, that means I have to recompile one more time. Sorry, I forgot one step. One step that I need to do is actually look at that moving average and decide how many days I want to do that over. So I'm actually going to do it just 3 days. Whoops, 3 days here, just for the sake of something different and interesting. And let's do that here as well. Moving average, 3 days. And that's where you have to define that here in modeling mode. And then that calculation of doing it over 3 days is buried and compiled into the model itself. Okay, so let's do this again. In the case this time here, I want to actually make this a little smaller. And I'm going to put the moving averages on their own graph here. And I can do that while I'm waiting. Well, this is actually almost done here. So let me wait till that gets out of the way. And then now I'm going to go define variables. There's my moving average. So I can drag that to a new graph. And then I will do the same thing here. And I'm going to set it to the same scale. 150. This is moving average. I think that's probably all I need for that one. And then we'll auto arrange that so that we can see what's going on. And I'm going to do the same thing again, 5 days. And we'll move the influent around and you can get the sense of how that works. So you can, as I mentioned before, do whatever you need to do in terms of calculating and running the, different types of analysis on some of these numbers. And here you can see the difference between how the daily average looks and how the moving average looks, right? This is carrying, the information along over a longer period of time, right? This is already starting to come down, but this is still looking 3 days into the past. Whereas this is only using 1 day of information as it goes by. So it's a way to kind of hang on to information, to have a little bit of a history of where the state of the process is, and use that in your control algorithms potentially. Okay, so let's move on back to the slides here, and I'm going to talk now about defining mass flows and integrated totals. Again, this is a relatively straightforward concept. Mass flows are things where we're going to basically say what is the mass that is passing through a particular connection point in the model per time, right? So it's basically the same type of menu functionality here. You click on the connection points where you want to do that, and then you can click on the things that you want to do it for. So this particular example showing that for both the effluent and the wastage, we're going to do a mass flow of solids. And basically the mass flow is calculated as the flow times the concentration of whatever it is you were doing here. Right, so that's going to come out in mass per time. So grams per day, because of course we're multiplying meters cubed per day times grams per meters cubed. This is the same as milligrams per liter, and it gives you grams per day. Now you'll find very quickly that the units of grams per day are not necessarily the most useful units to work in because they're almost always going to be a huge number. So basically what you do is you click on this little graph here, or sorry, pull down menu here where the units are, and then switch it to something that's more helpful, like kilograms per day or pounds per day or tons per day if you are working with a big enough facility. And just as a total trivia point, the reason it comes out in grams is because grams is the fundamental unit that we actually do all the calculations in GPSX. So that's why it pops up with that by default. Right, so the typical uses for the mass flow is basically sludge production. So in a lot of the training simulators that we make, and also in our SimuWorks program, we almost always put sludge production based on this exact defined variable, the mass of sludge that's being produced per time under the current conditions. Chemical requirements, like a mass-based chemical dosage kind of thing, effluent or emissions mass estimates, what is the actual mass of phosphorus leaving the plant, or the mass of carbon dioxide being emitted from the tanks. Those are numbers that you can click on and make a mass flow over time. Right. Okay. So the totalizer basically is something where you are going to integrate a variable over time. So it's called totalizer in the menu. It's actually probably should really just say total, but the idea is it's an integration of something over a period of time. And it's essentially where you want to add something up over the entire run of the simulation. So just to sort of put that in context, let's say, for example, we're running this 5-day simulation. And as you can see on this graph here, I have plotted the airflow into the aeration basin, and that is in meters cubed per day. I wrote it here big because this is a little bit small text. So meters cubed per day on this axis, right? And that's per day instantaneous rate at any particular time. So I did this one, for example, by just moving the influent around and changing the loading while I had a DO controller on. So the DO was changing the amount of airflow required over time. Right. Okay. So now we want to know what was the total amount of air that was used over those 5 days, right? So basically we're asking the question is, what is the area under this curve? And that will be in total meters cubed, because basically we're integrating something per day over days. And so that works out to basically essentially multiplying in a way that amount of air that came out. So in that case, it's meters cubed per day times days, which gives us a total meters cubed. And again, same functionality, pop in here. Now I was using the process variables thing instead of the drop down rather than the concentrations one, because I wanted to get an airflow. So I just click on aeration here, and then these process variables, there's my airflow at standard conditions. And that is what I integrated over time. And again, you're going to get a new variable here. So signal integration, total air to the aeration tank. And GPSX will construct a unit for you over here by multiplying these two things together. Now, this is obviously meters cubed per day times day. Now, if you pull down that menu, it will give you another option to switch that to just meters cubed, or in this case, I decided to flip it over to feet cubed, and you can see that it works with that number. So that is a useful thing to be able to do. So this is, just to reiterate, an integration for the entire length of the dynamic simulation. So for steady state, the answer will always be 0 because it didn't integrate anything over time. But for a simulation that you're running over a period of time, the longer the simulation, the more you're going to integrate, so whatever you decide upon, this is a useful way to sort of integrate and count the amount of something. And now the typical uses for this is basically, looking at how much of something was used up over a period. So total airflow or energy used in 1 week, you could do an integration on kilowatts and get kilowatt hours, so to speak. Now, kilowatt hours is something we already calculate anyway, so you didn't need to necessarily do a define for that one. But total mass of solids produced, how many tons would have had to have been hauled away? Cumulative cost under variable energy pricing, that's a really good one. Many of the training examples that we do around energy use this. So because the cost of energy goes up and down during the day, you want to be accumulating and doing an integration on dollars. Therefore, that way I'm capturing the right amount of money spent. And mass of nitrogen or phosphorus in the effluent over a month. I've done a couple of examples like this where you run the plant under dynamic conditions for a month and you have something changing, and then we're saying, okay, what was the total mass over that month that ended up in the receiving body of water? This one is another one, again, that requires you to do sort of inception, like a defined variable of a defined variable. In that case, you are doing a define of a totalizer on the mass flow of nitrogen. So you start by doing the mass flow first. So you go to the mass flow menu under the concentration, find ammonia, do that for your effluent, get that number. So that's now mass per time. And then you go back and do it again for the totalizer, and then find the defined variable that you had. This is the one that we just created. Check that off. And then that creates a new variable that is your mass. So this is not mass per time, but mass total, right? And so that's going to be the amount that came out the effluent in the whatever length of time period that you were simulating. Okay, let's take a look at doing that. All right, I'm going to flip to a new layout here. Let me go to this mass flow total example. Yeah, this is basically the same plant that we were looking at before. And now, instead, I'm going to go, let me see here, how am I doing for time? Okay, so it's half an hour under our belt. I'm going to go to the define function here. We're going to go to mass flow. And again, we can see all of those sorts of things. We're going to go to the nitrogen compounds this time. We'll go to ammonia, check that off, and we want to do that for the effluent as well here. Okay, so I hit accept, and now this connection point that I just checked off, if we go here, outputs, there's the defined variable, there's the mass flow. Note the concentration over time. I'm going to flip that over to kilograms just for fun now, because I know that's probably the unit that I'm going to want to work in. Okay, so I want to come over here, rebuild that thing. And I have a tab all set up and ready to go here. There we go. I'm going to go to this new variable, define mass flow, and we are going to just plot it on a graph. And I'm going to change the scale here. We're just call this mass ammonia, mass flow of effluent ammonia. Just make sure I get the right concept here. And you can see there's the units that I was using. I don't think I'll need to, I think I need to go more than 1 kilogram per day. Let's go 100. And let's just change that to a different color just for the fun of it. And I'm going to run a 5-day dynamic simulation while changing the influent again. And we can see how, of course, things are going to change as the loading to the plant changes. And we can see if I really ramp it up there, you can see the amount that's going out to the system is of course significant potentially over time. And again, this is mass per time showing here. All right, so now let's put a totalizer on that. So if I go back here, total. Now I have to go to the define variable that I did before. Here's the define menu. Now you'll see this is the list of things that have already been defined. There's really only one of them in this case. And so we'll make that, and then that now gives us a new variable here. There's the totalizer variable. So we'll pop back over, rebuild that. Should have done that together in the first turn. And I'm going to plot this actually as a separate setup here. I'm going to make usually when we're doing this, I want to kind of make the totals not as an XY graph, like a time series graph, because basically it's a number that just goes up over time as you're doing the integration, as you're accumulating things. So generally, I tend to want to put mass flows on XY time series graphs, but then I want to put a totalizer generally on the digital graph, right? So let's go to my new variables here. Let's go to that totalizer. And let's go here. And so you can see signal integration, mass flow, ammonia, nitrogen. So a define of the ammonia. So let's make this a digital graph. And I'm just going to rename that total mass. Yeah. And now this is again kilograms per day times day, so we can probably come up with a better unit than that. Let's flip that over to, well, let's just do kilograms. There's kilograms. Okay, so let's run the 5-day simulation like we did before, and I'll just adjust that up and down as we mentioned. And I'm going to ramp it up enough that we get some, it's not fully nitrifying. Let's get at least something interesting going out in the effluent here. And then I'm going to put this back down and we'll just let it get back to fully nitrifying here. So now it's fully nitrifying. This number's not going up very quickly, but it did go up quite a bit here. So the area under this curve is 41.5 kilograms. Right, now I've seen a couple of really interesting things that you could even take this, believe it or not, to like another level, which is this variable put onto our GPSX optimizer. So basically, you might want to give GPSX the ability to do step feeding, or maybe it's a total nitrogen number, and you want to build a controller about carbon dosage, and so on. In that case, you can do a dynamic run. You can integrate under the curve, and then what you want to do is make that number as small as you possibly can. In which case, our optimizer can do that. So there's many levels to what you can do to combine all of these things together to do interesting studies of control schemes. Okay, so that's those two. And then now to discuss the last two options, which is, oh, sorry, I have one more note that I did want to mention here. This feature that we have allows you to sort of specify any combination of connection points, any type of calculation and any variable that has. So we do say exercise caution and think through what you're doing, because it does allow you to define variables that may or may not have any kind of reasonable meaning. So in other words, you can make up the connection of a mass flow of pH, but that doesn't really have any actual meaning, right? Like, what is the mass flow of a pH? You can do a totalizer on a concentration, but that also doesn't really mean anything very useful either. And I also often say just check the units to think about what you've created if you're wondering. So if you did a totalizer on a concentration, you'd be multiplying grams per meter cubed times days. So you'd end up with gram days per cubic meter, which isn't really anything. So so just to keep that in mind, that's make sure you can check the units to make sure that you've created what you think you've created. Anyway, we do find this to be a very useful way to keep track of side effects in dynamic simulations, right? So I've done a couple of experimental things and studies where it was looking at trying to bring in extra load in the evenings when the energy was cheaper. And so this was a really useful way to do that. It was sort of accumulate the kilowatts and accumulate the dollars spent at different times of the day. So you needed not only to just look at the energy that was being used or the cost, you had to have that integration of the dollars when during the specific time of day, and to try and find out whether it was actually worth it to try and hold back some flow and then treat it more in the night. Right. Okay. So now we're moving on to the last one, the most detailed one, which is defining your solids retention time, SRT, and your F to M ratio, food to microorganism ratio. And these are a couple more steps to it than there are in some of the other things I've showed you before. But these are, of course, key process indicators. The SRT in particular, it's almost like basically the most important thing about your plant. What is the SRT? So you can define it in the way that means the most to you, and what is specific to your particular layout. So in general, when you do an SRT definition, we're going to create an equation that looks like this, right? It's basically the mass over the mass flow. So to calculate the mass, we're multiplying the volume of the bioreactor times the mixed liquor concentration. And we divide that by the wastage, right? Which is wastage flow, Q WAS, times the concentration of the WAS. So basically, that works out in units to be days. So you're going to say I'm multiplying the mass over the mass per time. When you divide those out, you get days. So that's going to say your SRT is 3 days or 8 days or 25 days or whatever have you. So now your choices about which of these numbers to use from your layout is the part where we want to be able to give you some flexibility. So as I mentioned, it does mean kind of different things to different people. Certainly there have been a lot of people who have insisted to me that you do need to include the effluent solids in the calculation of your mass flow. Those are solids that are leaving the system, so they should be calculated in. Some people like to include the idea of having clarifiers or not in the mass, and so on. So this allows you to define it in whatever way you like to work. So you can define an SRT for the whole plant, including all the multiple parallel trains, or you can split them into individual ones. You can include or exclude the mass in the clarifiers as you see fit, include or exclude those clarifier solids. And also you can do it for multiple definitions of SRT. So quite frequently we end up having a total SRT for the plant and an aerobic SRT only, right? And then some plants are very complex in the way that they track, and where they do their wastage from. So sometimes you end up having to click on multiple points in the layout to be able to pick up all of the places that wastage happens from. So the key point takeaway here is we don't define the SRT. You can do that in the way that you want. You can, in fact, define multiple SRTs, as I mentioned, total and aerobic, or you can have separate SRT definitions for different trains in the plant. I've certainly had that in the past where there's, a plant that's been upgraded and they have two different, a north side and a south side, and maybe the sides are not the same, so they need their own SRT calculations and so on. So those are all there for you to be able to do. So when you start to do an SRT definition, you'll bring up the menu from the usual place, but you'll see here it's a little bit more detailed. So you start out by hitting this plus button that's going to create a new SRT equation. And then you will give it a name. This is how we allow you to do different ones. So we have to have a unique name here. So you might want to call it SRT total. And then once you've done that, in this window right here, it's going to pop up a blank equation. We can see it's mass over mass flow. And then as you click on various parts of the plant, it will start adding parts to this equation. So when it looks like this, if you move the mouse around on your drawing board, you can see that it has a little hand and it has a check mark. And that means I have clicked here because this will add it to the SRT equation. Now, for plug flow reactors, when you do that, it gives you the option of whether you want to add them all or not. So let's say, for example, I added them all here. Then also I have to click on the place where the wastage happens from. And so this is going to be not the mass in the clarifier, but the connection point. That's saying this is where the wastage is coming from. And then now I have these details filled out using the labels, this MLSS and this WAS here to describe how we're calculating SRT. So here's an example where we've done it for two different ones, and this is what I'm going to show you here in a moment. SRT aerobic is actually not the full tank here, but only the second and third zones because those are the aerated ones, and we only want those for the aerobic. You can also control SRT directly from this menu. This is a somewhat less sophisticated controller. It basically does a very simple instantaneous calculation. To do that, you can specify where you want to waste from, what you want the set point to be, and what the minimum and maximum wastage amounts are. And then if this is checked off and turned on, then you can always know that it's going to, as best it can, try to move the wastage to a spot that will match that SRT calculation. All right, so once that's done and you've gone into simulation mode and the model's been compiled with your new equation in it, you then open up that same menu again to get back to where you can drag these onto graphs. So that's a little different than what I was showing you earlier. You don't go into the object to get the menu. Here you go back to the place where you defined it. And then you can just drag it right from there onto the drawing board and you can get a couple of different SRT calculations here. Now, I will very quickly point out this is dynamic solids retention time and then just regular solids retention time. The difference between those is that the irregular SRT calculation is done instantaneously every communication interval. And so if you have an instantaneous change in your wastage, it will show an immediate change in your SRT calculation. The dynamic one is meant to sort of smooth that out by not doing it sort of instantaneously, but more accounting for the movement of solids through the plant in a more dynamic way. So it actually integrates the movement of solids. And I won't go into all the detail right now here, but you can look in our tech ref to see how that works. Okay, and lastly, I will mention that the F to M ratio is almost exactly the same thing again. You can see here, you hit the plus button to create a new F to M variable, you give it a name, and then you click on various parts of your drawing board in order to define, first of all, the mass flow of the BOD, that is the food, and then the reactor that's containing your biomass, which is the mass of solids, so your microorganisms. So that's where you get your food and your microorganisms. There's your equation, and you're off to the races. Right, and again, because we have complex plants laid out in GPSX, sometimes you can do multiple F to M ratios. The most typical application of this is where you have separate parts of a plant with different trains, and I wanted to calculate the F to M ratio appropriately for each side of my plant, for example. All right, moving on to our final demonstration of the afternoon, I'm going to go over to this SRT example. Okay, so this is again the same plant and more or less the same thing, but we're going to do the example that I was showing you earlier, which is to define both the total SRT of the plant and also the aerobic SRT. So again, you have to be here in modeling mode. We're going to go here. We're going to go solids retention time. And then, as I mentioned, there's a little bit of a nice explanation up here how to do this in case you forget. Click here, and then I'm going to do total first. So this becomes the name of the variable. It starts with SRT, and then we add whatever label you want over here. So I do that. Now you'll notice that when I move my cursor around here, it actually has that little hand symbol to it. So I'm going to add for total the mass of solids in my bioreactor. So let's do that. I'm going to add all of those. And then I'm going to add my wastage connection point. And it's important to get the arrow pointing to the right here. You'll see there's a little plus symbol on it. And so now we can see its mass in the bioreactor over the mass flow of this WAS connection point, and that should do the job. I'm also going to add another one, which I'm going to call aerobic. And in that case, I'm going to, see it's blank again here. I'm going to do this one, except I'm not going to include the first reactor because that's the anoxic reactor. And same wastage connection point here. Okay, so that's them done. And so now we can go over to simulation mode. Well, one more time, we're going to let that thing do its job of compiling the whole model along with the calculations that we made. So I have a tab here available where I'm going to plot a few things. I set this up ahead of time. One of the things I'm going to do is actually plot the wastage flow here on this graph. So because what I want to do is do a bit of sensitivity analysis and a bit of control on this. So that'll be something interesting to look at. And then once this is done, I can then drag my newly defined SRT variables down to this graph here. Okay, so as I mentioned, rather than going to the objects themselves, you go back to that same definition menu, solids retention time, and I'm going to grab the SRT total and also the SRT aerobic and put those on that graph. Now you'll notice that each time I did that, I got both the regular instantaneous calculation and the dynamic one. I am going to remove the dynamic ones just for the sake of clarity here. You can do whatever you might want to, but if you just right click, like just right on the words there, right click, remove, you can get rid of them that way. You can also go to the gear thing up above and do it there too, if you like. Okay, so that is in good shape. We can now have our two different SRTs. So the aerobic one will be in blue and the regular one will be in black. Okay, so what I want to do is I want to set the scale on this because I know that we don't need to go up 1,000 days SRT here. So I'm going to set this to 25, and that should be good. And what I want to do is run a analysis using the analyzer button up here. And what I want to do is just change this wastage control number, which is currently 40 cubic meters per day. I want to run that at a bunch of different values from low to high, and then see what the effect is and how SRT will be affected by changing this wastage rate. So I have that actually kind of nicely set up in a scenario here called sensitivity. I also will knock down the temperature a little bit to sort of just highlight the effect of running at different SRTs a little more strongly than it was under the default temperature. Okay, so now I want to do analyze, right? So I have to make an analyze feature here. I will mention, of course, we've done many different sensitivity analyze examples in a lot of our webinars, and a couple of them that focus specifically on this. So if you want to know more about how to use the analyze feature, always check out our YouTube channel. So we're going to run steady state simulations starting at 20 meters cubed per day up to 100 meters cubed per day. And I'm going to turn on the steady state analyze mode and start it up. And so what it'll do is it's going to run one simulation after another here. And it's going to start plotting the wastage here. So as I mentioned, we started at a low number, and then every simulation it increases it, and it goes up to a high number. And it solves solves the model at every step along the way while it's changing this input. Now, the interesting aspect here is you can see, of course, those SRTs that we calculated are, of course, going down as we are wasting more of our solids. So this is kind of an interesting example because we can see here, because we're plotting both the total SRT and the aerobic SRT, that this line right here is 5 days of SRT. So at the very end, at wasting the highest amount, we can see that our total SRT is a little over 5 days, but the actual aerobic SRT is under 3.5. So if I go over and take a look at our effluent, of course, it's calculating, the whole model on all the calculations there. We can see our effluent ammonia is no longer 0.6 or whatever it was when we were doing the earlier examples. It's now actually impacted here. It's up to 2.6. So that's an example of where being able to look at both SRTs. If you just looked at the total, you might say, oh, 5 days, that's probably pretty good. Well, actually, the aerobic was less than that, and it's actually right at that kind of sensitive area that we go through there. Okay, so what I'm going to do now is I'm going to reset that model. I'm going to actually switch this back to a slider. And I'm going to switch to a dynamic simulation now. Oop, I got to turn the analyzer off first. Thank you for reminding me. Dynamic, yes. Okay, I'm going to reset that one more time. Just make sure it didn't mess anything up there. And what I'm going to do now is we're going to run a 5-day dynamic simulation. Now, in this scenario, rather than having a constant influent, we're going to actually read an influent from a file. And this is what it looks like, as you probably know, when you're reading GPSX data in as an input. So all of these things are going to dynamically change during the 5 days. Most of the concentrations are just going to change once per day, but the influent flow is going to change every 15 minutes. And so that way we get something interesting happening as we run this. Okay, so now what we're going to do is we're going to run the 5 days, and we're going to see, because now we're working with a constant wastage flow. We're going to see during this dynamic event how the SRT changes if we don't change anything else in the operation of the plant, right? So now we can see that the SRT kind of moves around, right? That seems reasonable. The loading is changing, the flow is changing. So that means that things are going to be different in the plant. There's dynamic effects happening. We can see here that it kind of bounces around. It's not too terribly different over the period, but there is a period right here where the loading changed a bit, so that under a constant wastage rate that our SRT went up for quite a while. We were probably holding more solids than we really needed to. So therefore, we can see that there's some effect. Maybe there's the opportunity to do some control on this in a little bit better way than just holding it constant, right? So I'm going to pop back to modeling mode as the last example here. And I want to build a SRT controller around that SRT variable that we had. Right, so I am going to go into the clarifier, and as you may know, in our control section here under this pump control, rather than just using this value, I can actually turn on a controller here, and you have to go and tell it what is it that we're trying to control. And we have some other YouTube channel videos here, other previous webinars that show more details about how to do this. But in this case, I want to highlight the fact that I'm going to do a controller on our total SRT number. And we're going to do it so that it takes an action every 15 minutes. And then we would need to tune it and give it some more details. Now, one thing that we have to do is this controller effect on control variable. This actually needs to be off. What this means is, do the control and manipulated variables act in the same direction, or do they act in the opposite direction? In this case, for an SRT controller, same thing for a mixed liquor controller, they act in opposite directions. Increasing wastage decreases your SRT. So this needs to be off. Now, it just happens to nicely work out that these numbers are okay for tuning. The reason is that our wastage is a number like 40 and our SRT is going to be a number like 10. So they're in the same order of magnitude. So our gain, excuse me for a moment here, I'm losing my voice a bit. Our gain is actually okay to be around 1. Those are in the same orders of magnitude. So I'm just going to leave that without going into a lot of details. Of course, tuning your PID controller is an important thing, and maybe you would have to do that if your situation was different. Okay, set point for control variable, this 8 days. That's what I've decided that we're going to do here. Save that, go back to modeling mode, simulation mode. Now it's going to build that controller and the controller is acting upon the newly defined SRT that we did. So, and then I'm going to run that same dynamic simulation again, and we'll see if it does a little bit more smooth control of the system. So I got to wait for this to finish compiling, and then we're going to go to our dynamic simulation here. Select scenario, dynamic. So all these things changed over because they're now ready to read in the data. And let's do 5 days. So if we look down here, we can see the SRT total that we were looking to do is in black, and we're shooting for 8 days of SRT. So we can see here, it's actually hanging around 8 reasonably well. It's actually much tighter control than what we were doing previously. And maybe if we did a bit of work on the tuning, it would be even better. But the way that that's happening, of course, is now instead of having a constant wastage of 40 or 50 meters cubed per day, it's now allowing that the controller's changing those sorts of things. And it adjusted during that period of low loading by wasting a little bit more solids rather than holding them back. So it's actually keeping that SRT a little closer. It's not perfect, but it's a little flatter than it was before. All right, so that kind of gives us a feeling for how SRT works. I got one last example of F to M that I'll very briefly go through here. And so lastly here, I'm just going to do F to M just to show you what it looks like. Food to microorganism ratio. Oh, I'm sorry, I did not delete it out the last time I did it here. Let me do that, and I'll create it again. So in this case, I want to do F to M. You can call it whatever name you want here, and then now we can see it's a mass flow over the mass. So in this case, the mass flow is like the amount of BOD coming in. So that's this stream right here. So I'm going to add that one, and then this bioreactor. So therefore is our mass flow over our mass. And then we're going to go over here. Okay, so what's happening is I got a graph up here ready to go for our new F to M calculation. And just like we do with the other ones, like the SRT, once this is finished compiling, I go to this define menu again. I grab the new F to M calculation, and I'm going to drop it on this digital graph in this particular case here. So drag that over here like that, and then I can run this to steady state, and we should get a reasonable number. 0.25. Now it's 1 over days. What this really means, of course, is it's going to be pounds of BOD over pounds of VSS per day. And so that way you can see that it's going to be pounds over pounds per day. And that's what this works out to. So that's a number that's, maybe a little on the low side for the example that we have. But nonetheless, you can do that as much as you need to. Okay, well, I'm getting to my point where I'm running out of time. I'm just going to wind things up here with a few final thoughts. So this is obviously a very open-ended kind of system for doing this. You can click on pretty much anything you want to click on and do any sort of custom type of calculation. So one thing I will mention is that some unit processes, it's a little bit tricky in terms of understanding what the calculation works out to be. So the main one that's always a little bit a matter of interpretation is what you get when you do a calculation of SRT on a biofilm unit. So by that, I mean, let's take an IFAS unit, for example. So you got plastic media floating in there, and it's got biomass in the liquid and also biomass on the media itself. And so if you do the SRT calculation exactly the way that I showed you, it's going to count the mass on the media as well. So you may end up with an SRT of a really long number, like 100 days. And so, and I'm not, it's sort of open to interpretation. It's not precisely wrong. I mean, if you were to completely ignore the biomass on the media, then you might end up with a very low number that is also not really representative of the amount of biomass in the system and what their residence time are. So SRT of a biofilm system really is a matter of interpretation that you would like to sort of think about. So what I often recommend people is if you have some other way that you would like to calculate the SRT of a biofilm system, based on whatever it is that your interpretation is, you can always use our Axel regular custom coding language to be able to build that calculation rather than our define function. And lastly, the SBR. That is also a bit of a tricky situation because, of course, the WAS, the wastage flow out of that SBR, is only active during part of the cycle. So if you do a regular SRT calculation on it, you'll see the SRT go up and down. And in fact, it might be, an infinite number during periods where there's zero wastage at all. So often we try to do it differently by maybe just calculating the total average of the mass in the SBR during the whole cycle, divided by the mass flow of the wastage of that. And then so you have to maybe do a little bit of a custom calculation there. Okay, lastly, just wind up by saying that our define function basically allows you to create custom, additional parameters that meet your needs for the particular plant you're working on and the way that you like to define things. And that is the goal of this particular feature, is to allow you to customize things in the way that you want them to work. So all of this stuff, everything that you do with a define function creates new variables that are automatically added as new GPSX menus, and then therefore they can then be used in exactly the same way any other GPSX variable is. So plot them in the way that you want, export them to reports. You can also use them as control variables, just like we did in that SRT example, and put them on the analyzer or the optimizer. So they're all there to be used in that way.